In this example, we're going to test out moment of inertia. The question reads, we have 6 small brass and aluminum spheres connected by these lightweight rods to form a rigid object like a jack. Tells me the rods are joined about their centers, just giving you some idea of the shape. What I have highlighted here is all spheres are the same distance, so they're all the exact same distance from the center. So this distance, all of those distances are the same. Now, as it goes on, it says the brass are shaded in the diagram. The aluminum spheres are unshaded and they have less mass. So let's highlight all the ones that have less mass. So there we go. So there's my less mass. Now we saw in class, the farther your mass is away from your axis of rotation, the more moment of inertia you have. Also, we saw from class that you just add up the moment of inertia for each particle. So for this first one, I could do each one. Now these two, that's my axis of rotation, so those have 0r. They're 0 distance away from the axis of rotation. But here, this particle has a mass away, this one has a mass. So the I of each of these, this is going to be mr squared, this one's going to be mr squared, and mr squared. So this problem ends up with 4mr squared. Now granted, I have to be careful because these are all the shaded ones in blue, so these are all less mass. Okay. The next one, again, these do 0 because they're 0 distance away from the axis of rotation. So I have 2mr squared of the light ones and 2mr squared of the heavy ones. So I know that this is, again, I could add them up, 4mr squared, but it has to be a little bit bigger than 4 because these masses are bigger than the previous ones. Okay. The next one, this is again 4mr squared, but it's a little bit bigger. If we looked at the previous one, it has 1, 2 of the blue spheres which are less mass. This one has 1, 2. They're all the same radius, so that means B has to equal C. They're evenly distributed. Last one, it is 4mr squared, but it says all of these masses are larger, so this is much larger than the original A. So the answer choice would be D is greater than B equals C greater than A. How I could describe this is D has more mass at a greater distance from the axis of rotation. So again, all of them were 4mr squared, but certain ones had more mass. The masses of them were different, so I went with the one that has more mass, the greatest distance. Let's take a look at our next problem. So in this problem, give it a shot for yourself first before I give my explanation. You could even pause the video. Here, what we're going to see is the moment of inertia greater about the left end. So if you think about it, if you were to hold the rod right here and spin it all the way around, is it greater if you hold it on this end and spin it around, or is it have more rotational inertia if you were to hold it in the middle and spin it around? Okay. Let's start with the left side. So holding it about the left, we see that I have, break it down into different pieces, that I have the 3M, okay, and it's almost the entire length of the rod. So I have I about the left, so I have the 3M times almost the whole length of the rod squared, plus I then have the 2M, okay, that's about the length over 2 squared, plus the last one, this mass is pretty close, so when the mass is really close, you know, if the length is close to 0, then that one's almost 0. So really we're just looking at those two. Okay? So I had a lot of mass on the outside. Okay? Looking at the next one, okay? If I look in the middle, okay? Now, right here, almost all this mass is 0, so I don't have to worry about that. So now I about the middle, I have the 3m, but what's its length? It is the length over 2. It's only half the length of the rod now. Plus the m, which is also at length over 2. So quickly I see, comparing these two, that I of the left is greater than I of the middle. Okay? Because this one has the 3m, but it's at the whole length. This is 3m, but it's only at half the length. After that, I have the 2m at half the length. This is only m at half the length. So the first one about the left is greater. My last strategy here. Okay. Let's look at about the left side. Well, again, this one we're going to say it's close, so that's 0. So then I about the right, I'm only going to look at the 2m, which is the length over 2 squared, plus m length squared. Okay. So which one has most of the mass farther out? That is, I about the left is going to be the greatest. Okay. Again, the basic understanding and how to explain that. Okay. I about the left is greater because I have more mass at a greater distance from the axis of rotation. Here's another problem. Again, give it a pause, try and compare. I'm trying to see which has more moment of inertia. Is it the cylinder or the ring? It says they have the same mass and they also have the same R. Okay? Just looking at it, you should see this one, all the mass is located at distance R. If I did this one, well, if we think about it, I have the ring, okay? So I have some of the mass out there, but then I also have the inside of that. So if I did this one, I of the ring must be greater than I of the cylinder, okay? Because more mass farther from axis of rotation. If I wanted to check back to that, let's see. Okay. If I look on this page, okay, here is I of a ring, and that is mr squared. So it's saying essentially the k value, or the number in front, 100% of the mass is at the radius. If I looked at a cylinder, essentially by doing some calculus, I end up and it says only half of the mass is acting at the entire radius, because the other mass is on the inside, so it has a smaller R. Okay. On to the next one. What happens if I remove the center? Well, in this problem, all of the mass is at a distance R. Okay. Here, I still have a ring, but I now have removed some of the mass, right? I took that mass out. So let's call this A, B, C. So I of C is the greatest because it has more mass on the outside. Then I would say I of A, okay, and then I of B. Okay. Why is C greater than A? Okay. C is greater than A because both have all their mass at the radius, but C has more mass. B is the least because it has less mass and it is closer to the axis of rotation. So this next example is why we have to be able to do I. So here it says a teenager pushes tangentially on a small hand-driven merry-go-round to accelerate it from rest to a frequency of 15 RPMs in 10 seconds. So I have a merry-go-round, and I have a force being pushed on it tangentially. It gives me the radius, it tells me its mass, and it says I have two children sitting on it on opposite edges. So this is like the Google Maps, the top view. So there's one student's head, and here's another student's head. Okay. Calculate the torque required to produce the acceleration neglecting frictional torque. So this is where you have to do now a torque net statement equals I alpha. Okay. This is I of your system. Okay. So if I had to do that, this is the only force that creates a torque. Gravity and normal force are going into the page and out of the page. So if I look at, that's my R. Those are perpendicular. So this would be force perpendicular to R equals I of the system times alpha. So the most challenging part of this problem is you are going to have to find I, moment of inertia. Now it gives you I of the merry-go-round. So that one's pretty easy. Okay? But what do I do about these two people sitting on it? Okay? Well, I of the system, or I net, equals I of the merry-go-round plus I of kid 1 plus I of kid 2. Okay? Now, why can't I just add their masses up? Why can't I just say I net equals 1/2 mass total times R squared? Well, we learned in class where the mass is distributed matters. So on this one, I noticed that the students or the children are all the way outside. But this is for an even distribution. Okay, this would only work if you were to take the students, smash them down into a pile of meat, and evenly spread their mass over the merry-go-round. That's disgusting. We won't do that. So now we have to look at it differently. So when I do an I net, I need to do I of merry-go-round like we saw, plus I of person 1 or kid 1 plus I of person 2. Okay. All right, so this is going to be half mass of merry-go-round times the radius of merry-go-round squared plus I of the person. Now the person is like a point particle because all their mass is exactly at that location. So I would do mass of the person times R of the person squared plus mass of the second person times R of the person squared. If you notice, they had the same mass, so I could change this a little bit more and say this is 2 mass of the person times R of the person squared plus 1/2 merry-go-round times its R squared. So that is why we need it, just to be able to solve I. Okay? After that, the problem gets simplified down a little bit. Okay? Whoops. Now I can find I, so I could plug my numbers in. Well, let's actually plug those numbers in. I'm going to pause it and come back. So here I can see I plugged my numbers in. Okay. This was a squared. Check your math, I've just rounded. That is my moment of inertia. So all that was just to be able to solve for this circled I. You have to be able to do that. So now I have the force is what I'm looking for, times R, the radius was 2.5 meters, times I, which we said here was 2690, times alpha. On this, I would have to do some rotational kinematics. So you could, again, pause the video and try that. I'm going to pause it, and you'll see my work show up right above. All right, here you can see I did my kinematics. I solved a kinematic equation for alpha, and then plugged it in. From there, I can do my algebra to find the force, and I got 169 newtons. So this is the type of thing where if you can't solve I, you're going to be in trouble. And you just have to know it's I net, adding it all up. Okay? We'll have lots of time to practice, but make sure you're prepared for that.